Hey everyone, welcome back to the MetaLogic Podcast. I'm your host, Aditya and this week I'm happy to have Ryan Goyle back here with us to talk about deep learning and artificial neural networks.
Hey, Addy, thank you once again for having me. I'm pretty excited for today's conversation because we're going to be getting into the technical nitty gritty on how artificial neural networks work. Specifically, we're going to be talking about one type of artificial neural network, that's the feed forward ANN, also known as the multi layer perceptron. So I'm pretty excited. I want to see how this conversation goes and if we are able to demystify how something as technical, as sophisticated as this actually works.
Yeah, and this was a topic that we chose because deep learning is a term that's thrown around a lot, but very rarely does anyone actually explain what deep learning is and the different types of neural networks and how they work. So I'm also excited to really get into it.
So, Addy, before we get into what ANNs are or how ANNs work or the math behind ANNs, I thought it would be interesting to start off today's conversation by understanding why it is important to even study about them or why it is important to understand how ANNs work.
Why artificial neural networks or deep learning in general is such a hot topic and people want to learn about it is because it's the algorithm that is behind some of the most common and most exciting technologies that are there in 2020. The main one being autonomous cars. So when you think of Tesla and Waymo and the work behind autonomous cars, that's all being done with deep learning and neural network algorithms. Another classic example would be fraud detection. So in cybersecurity or in banking, the fraud detection algorithms to go out and find which transactions are fraudulent and which are okay. That's all being done using artificial neural networks. Generally speaking, though, these neural networks do work better when you have a large amount of data as compared to traditional machine learning models that work better when you have smaller amounts of data. But these deep learning algorithms are um, I would say not easier to work with, but they do stuff like feature selection and feature extraction automatically. So it takes out another person that needs to choose the variables that are important. It's part of these algorithms that are making those decisions.
That's a good point, Addy. But I think it might be helpful to talk about what an artificial neural network even is in the first place before we get into more sophisticated technical things such as feature extraction and feature selection.
Yeah, so artificial neural networks are a type of deep learning model, as I've mentioned already, and it's used specifically for regression and classification problems. Today, we're going to be talking specifically about feed forward artificial neural networks, which is a type of artificial neural network, and we'll get into what the feed forward portion means shortly. But there are different types of deep learning models, such as CNNs, which are convolutional neural networks, usually traditionally used for computer vision, and RNNs, which are recurrent neural networks, which are usually used for time series analysis. But today we're going to be focusing on feed forward artificial neural networks. So let's get into the nitty gritties of artificial neural networks and how they actually process data.
Yeah, so I think the first thing that we need to understand is the topology or the structure of an artificial neural network. Now, the word artificial neural network itself gives a hint that it has something to do with the human brain. And the whole point is that it is sort of structured similar to the human brain, in which it strings together multiple nodes or multiple neurons. So let me explain it in more detail. So an artificial neural network has, for sure, it has an input layer and an output layer. Okay. So in the input layer, you have certain number of neurons or nodes. Now, the number of nodes or neurons that you have depend on the number of features that you have and the types of features that you have. So let's take an example. Let's say you're trying to predict whether an airline or a flight is going to be delayed or not delayed. So Predicting delay or not delay is the output, but you're going to have certain input variables or features, such as let's take two. The first one is the probability of rainfall, and the second could be the flight carrier. And let's say the options for the flight carrier are United and Delta. So how the input layer works is it has the same number of nodes as you have input features. But if you have a categorical feature, then the number of nodes are equal to the number of levels in the categorical feature. So in our specific airline example, you would have 3 nodes in your input layer. And let me explain why. Your first node is going to be
before you get there, do you want to give a very short summary on what the difference is between a categorical feature and a numerical feature? I know it's really simple to us, but could you go into that?
So I think it would be best explained with an example. So your numerical feature could be like a discrete or continuous numerical input. So think of it as numbers, and these numbers don't represent classes or categories, but they're truly numbers in themselves. So when you think of rainfall, probability of rainfall, there's a 70% chance that it's going to rain today. That's not a class, that's not a category, that's a number, that's a decimal number, right? So that's a numerical feature. A categorical feature can be divided into what we call nominal and ordinal, but I don't want to bore you guys, but essentially what it means
But it's a category. It's in the name.
It's a category, yeah. So it's Delta or United. It's green, blue, red. It's first standard, second standard, first grade, second grade, third grade. Like they're categories. They're not numbers in themselves. So yeah, so back to ANNs. What the number of nodes in your input layer is equal to the number of input variables that you have, but for every categorical variable that you have, you're going to have one node for each level of your categorical variable. So in our airline example that I just briefly mentioned, you're going to have one input node for your probability of rainfall variable because it's a numerical variable. But for your second variable, the flight carrier, you have two options within this, United and Delta. So you're going to have one input node for each option. And these take the form of a dummy variable. So in total, you're going to have 3 different input nodes. So let's say there's a 70% chance of rain and you're taking a United flight and you want to predict the probability that it's going to be delayed or not. In this case, through your first node, which is your first input node, it's going to 0.70 is going to be passed in as it is. And in your second node, which is going to be United, it's going to be a 1 because it is a United flight. And the third node, which is the Delta, it's going to be 0 because it is not a Delta flight. So that's how your input layer is structured.
And moving on to the output layer, you can kind of think of those dummy variables as on-off switches, right? You only turn on the one variable if in this case it's a United flight, and the rest of them would be 0.
Exactly. And how an output layer works is also dependent on the sort of problem. So if you have a classification example, you're going to have as many output nodes as you have classes in your output variable. I'll explain this in a bit, but if you have a regression problem, you're going to have one single output node. So let me explain what I mean by that. If you look at our example, whether a flight is going to be delayed or not, you have 2 options, delay or not delayed. So you have 2 classes in your categorical output variable. So you're going to have 2 nodes in your output layer. But in a regression problem, if you're trying to predict the price of a house, you have one number that's going to be a prediction. In this case, you have one node in your output layer. But why ANNs are actually interesting and where the ANNs actually drop power is that there are some layers in between the input and the output layer. And these are called hidden layers. Now you can have one hidden layer, you can have 2 hidden layers, you can have 50 hidden layers. And you can have one node in each, you can have 2 nodes in each, you can have 5 million nodes in each. Now it really depends on the problem. It really depends on the structure that you want. But yeah, so what hidden layers do essentially is it takes information from the input layers, does something with that information, and passes it on as an output. Okay? So
and
every node.
What do you mean when you say does something with that information?
Okay. Before I get to that, just know that every node in an artificial neural network is indirectly connected to every other node in an artificial neural network. So let's say you have one hidden layer, one input layer, and one output layer. All the nodes in the input layer are connected to every single node in the hidden layer, and every node in the hidden layer is connected to every node in the output layer. So, and the information only flows in one direction, from the input towards the output. It does not flow back, which is why it's called a feed-forward neural network. So back to your question, Addy, what do the hidden nodes do with the information? In the hidden layer, in the nodes in the hidden layer, you have something called activation functions. These activation functions, think of them as processors. They take the information coming in, so from the input layer, and they perform some mathematical operation to that information and pass the output to the next layer, which could be another hidden layer or it could be the output layer. So let me give you an example. So let's say, again, we have three input nodes, right, in our flight example. And let's say we have one hidden layer with one node. Now, the information from these three input nodes would all join the one node in the hidden layer. When it joins, these joins from the input layer to the hidden node have weights. Okay? And these weights essentially, they essentially control how much weight is given from those input nodes to the rest of the neural network. So these connections have something called weights, and the hidden nodes themselves have something called a bias. So the weights on that lie on the connections get multiplied with the inputs that come on along those connections. Okay, so uh, once they get once each of the inputs get multiplied by each of the weights that sit on connections, they then get added together. Once they're added
And
together, the bias, yeah.
so before you continue, where are these weights and biases that you're talking about coming from?
Yeah, we have to get to that later. First, let's break down the structure itself, and then just assume that we know the weights and biases for now. So once the inputs get multiplied by the weights on the connection, they get added to, like, this whole weighted inputs, or the three different weighted inputs get added together to form a sum. Now this sum is what enters the hidden node. This sum enters the hidden node. A bias that rests within that hidden node is added to the sum, and then a mathematical operation is performed on it. Now, this mathematical operation could be a logistic function, it could be a ReLU function, it could be a softmax function. It really depends. So it's whether you want the output to be linear, it's whether you want it to be between 0 and 1, in which case you would use a logistic function. And yeah, so this really depends on the problem. This really depends on the type of data that you have. But you do have multiple forms of mathematical operations that perform some form of process to the weighted inputs and bias that comes into the hidden node. So once the mathematical operation is performed on whatever information comes in, it then gets passed on to the next layer, and then gets passed on to the next layer, and then gets passed on to the next layer. And
So
similar steps are done in each
it
layer.
becomes the input for the next layer. Your output of your logistic function or your whatever activation function that you use, that output becomes the input for the next layer. And the same thing happens.
Exactly. And it follows along until it becomes an output in the output layer, and that's when your neural network ends. So back to your question, you asked me how do you get the weights and how do you get the biases, right? To understand this, so these weights and biases are calculated or estimated during the training of a neural network. Okay, so to train the neural network, you need something called a cost function. And for example, one example of a cost function is sum of squared errors or mean squared errors. Or it could be anything that tells you how far your actual values are from your predicted values. Okay, so let's say so these weights and biases are initialized in a certain way. So you could choose them at random, or you could have a specific initializer that chooses them at 0. You have multiple types of initializers, and I don't think it would be productive to get into them. But what happens is, let's say they're chosen at random. All your weights and all your biases are chosen at random. You have one flight data observation that gets passed on through this ANN that has random weights and biases, and it gives a prediction at the end. and you know the actual value of this observation because it's a part of your training set. So now you can see how far off your actual value is from your predicted value, and this forms something called the error, right? So what the neural network tries to do when estimating the weights and biases is a process called gradient descent. You want to try and minimize your squared error. You want to minimize your error. You want to be as close as possible to the actual value. But gradient descent uses a lot of compute, and it's very, very, very difficult to actually reach the bottom of a gradient. So instead, it does a process called backpropagation, which is it's like a cheat code gradient descent. It tries to estimate a gradient descent. What this does is it takes the derivative of the cost function with respect to each weight and bias. So essentially, what this means is it understands which weight or which bias or which combination of weights and biases are most responsible towards the cost function. So if changing weight one would really affect the cost function, you want to change weight one. If changing weight three will not really affect the cost function, you don't want to change weight three. And so one by one, each observation is passed through the ANN, and after each observation is passed, the weights and biases get iteratively adjusted until it sort of optimizes or it sort of converges into what the algorithm thinks that the gradient descent would have achieved anyway. You know what I mean?
So we're actually bringing back like high school calculus. If we remember, like in high school calculus, we learned that the derivative of a function tells you the change in that function. We're doing the same thing here. We're looking at the
Exactly.
derivative of the cost function to tell you which one of the inputs had the most amount of change on your output. So it's kind of funny to me that we're
Yeah.
finally bringing back something from high school calculus. But no, it makes sense that you're basically going back and you're looking at which inputs change the output the most, and how much did it change it by, basically, and then changing that to make sure the error reduces and reduces.
Exactly. And you might be asking yourself, why don't you just keep running the neural network until the error becomes zero? And Addy, if you want to say a few words on this.
Yeah, and you kind of highlighted to this too before, but running neural networks is highly compute intensive, and eventually you reach this point of law of diminishing returns when it comes to computation power versus the lowering of error in your neural network. So you want to have your error obviously be lower, but it can take a long time to get to that point. So you got to weigh between how much time it's going to take and how much benefit am I going to get. Secondly, this sum of squared error only refers to the error measured in your training data set. And we've highlighted this phenomenon before in other podcasts, but the term overfitting comes into play when you start to tune your model so much to the training set that when you feed it new information for the first time, it's actually off, because the model that you created is so attuned to your training set. So you have to be careful of overfitting, and you have to be careful of the computational power that it takes for these models.
Yeah, so Addy, I know we touched on this a little before, but could you explain why you think artificial neural networks are popular? And perhaps if you can give a few examples of how they've been used in the past, that would be really helpful.
Yeah, so after going into these nitty gritty details, I hope you can see that neural networks tend to match the way humans learn, but they can deal with the data that us humans can't actually interpret. In essence, what a neural network is doing is taking in information through the input layers, making assumptions about that information, checking how close the assumptions were to reality, and then making changes to our assumptions to reflect that reality. So making changes to the weights and the biases. This analysis of weights and biases allows the model to see hidden patterns and unknown importance in the models that humans wouldn't be able to do. So that's why it's so popular and so powerful. It allows us to do stuff that humans weren't able to do before. And finally, we have the computational software to allow it to run. So you might be saying, like, what are some companies that are actually using this? So ANN is so widely used across many different industries because of its versatility. One huge success story is Sephora. So Sephora is a brand that they have products, beauty products for the most part, and they were able to utilize artificial neural networks to target its marketing to more distinct audiences. So they were using attributes such as location, age, economic status, purchasing patterns, and other business information to curate email marketing campaigns to attract more customers. So this way that they weren't wasting money on very broad marketing campaigns. Everything was targeted, and that led to an increase in profit. Second, Starbucks also uses artificial neural networks in their targeting marketing campaigns to help increase traffic onto their app. So when they launched their app, they wanted to make sure that people who were using the app, everything on their app was customized to them. So they weren't getting broad coupons. Everything was for what products they had bought in the past and what they thought that they could buy in the future. And they did a study, and it showed that their artificial neural network ultimately helped increase their revenue by $2.56 billion.
I think these examples are really interesting because they're very unlike typical data science examples that you see in like articles online and like newsletters and so forth. Like you typically see very technologically intensive companies such as like Tesla or GE that you think do deep learning, but you have companies that like Sephora and Starbucks too, and that shows how widely used this algorithm actually is.
Well, I think that sometimes we fall into the trap, even with us two talking, when we only talk about the Ubers and the Teslas, but then, like artificial neural networks, you can see the versatility that beauty companies and coffee companies and so many other industries can use this technology.
Exactly. And also at MetaLogic Consulting, we also do use artificial neural networks or multi-layer perceptrons for manufacturing companies. And one of the biggest use cases for artificial neural networks are predictive maintenance, internal or external. So this could be helping manufacturers sort of predict when their machinery would require maintenance. So now they could predict failure and they could be proactive. They don't need to react to failure. This could help them save costs, prolong the life of the machinery, and so forth. And also, they could do this externally. They could provide their customers. So let's say you're selling a Dell laptop. Okay, we could help Dell like tell their customers or their clients when they think their clients would require maintenance. So now this helps like bolster a user experience, reduces maintenance, it reduces warranty costs. So there's so much value that can come out of something so simple as maintenance.
Yeah, and maintenance is just one of the ways that we use it, but it's a very clearly we're really clearly able to see the value that ANN brings to maintenance and to warranty adjustments and stuff like that. As we wrap up here today, I hope that this conversation we had was helpful in demystifying the world of neural networks, of deep learning, really helping you understand that this isn't very complex once you get into the nitty gritty details. I think conversations like this will help you understand how deep learning and artificial neural networks can be applied to so many different industries and so many different problems. Uh, Thanks, Ryan, for being here today. Do you have anything that you want to add on before we end our conversation?
Yeah, just a quick note. I think it is important to tell our audience and tell our listeners that what we covered today about artificial neural networks is just a quick introduction and a quick and dirty overview of what ANNs do. But if you want to get into even more nitty gritty mathematical fundamental details, that's when that's when you can actually see the true power of ANNs. When you get into the parameters, when you get into the tuning, and we might make a podcast on this in the future, but that's truly when you see how powerful ANNs actually are.
Yeah, We started off by saying this, but there's a reason why ANN is being used at the world's biggest companies for so many different applications. It is one of the most powerful algorithms out there. And you're right, we didn't really go into like the very specific details, but this was a great conversation about an overview of ANN. But yeah, we look forward to bringing you, more episodes where we can go deep into the nitty gritty details to show you, and other episodes about different topics that we have. Thanks, Ryan, for being here today, and I hope that you have a great day.
Thank you for having me, Eddie.